Laplace transforms. Perfect. Now, the mathematics behind Laplace transforms is very sophisticated. I do not want you to get Laplace transforms as, how do you say, all the nitty-gritty details about inner measures, Lebesgue integrals. No, I don't want. I want you to understand what they are from an intuitive perspective, as extensions of Fourier transforms. I bet that several of you saw Laplace transforms before. My take is that they are a useful tool for engineers because they will enable you to do computations. So from an algorithmic perspective, they are a useful tool, okay? From a mathematical perspective, they are very, how do you say, complex animals. We do not do the mathematics, we do the understanding, okay? Perfect. Because in a certain sense, Laplace transforms will enable us to do computations in a good way. We will see how we embed Laplace transforms for the forecasting problem. Laplace will be a tool for making forecasts. So let's start with an introduction. I uploaded the stuff this morning, so you didn't see the PLOs. I'm pretty sure that you know all the stuff that is needed. Also because we are going to work from an intuitive perspective, not from a mathematically deep perspective, okay? So don't worry. I think that you know about complex numbers. That is the most important thing. The guy saw French Revolution and was with Fourier. They were also embedded in the scientific, how do you say, team during Bonaparte, Napoleon's quests. And there are some videos that I think are excellent, explaining from a visual perspective what is happening. I think you might want to watch those videos too, okay? I'm going to go through something that is kind of resembling, but extending, okay? So this stuff here still will give you some information more than what I say. And what I say gives information more than what they say, okay? Together, so it's complementing the information that I say here and in those videos. Why, what, how, and we do an example, okay? We do? So, model predictive control. How much do you feel about this? You want to find the best action so that somehow your trajectory is the one that you want, and potentially you want to also place a cost with it on the trajectory and how much fuel you will use. This kind of MPC thingy, how clear is it? Very much clear, not at all, kind of. That's for me to see. I see several tools and some trees. Is the tree related to this formulation here? So ignore this formulation. Whenever I say you this intuition that we have about we want to use F, or better, the dynamics as a forecasting tool, and we select the action that makes my forecasted trajectory the closest that I want. This concept here, is it clear? Perfect. So for now, do not worry. This one we are going to re-see it later. Whenever we do LQR, we will also see this one better. For now, the important is that I might want to find my best action to do through propagating forecasts. Here we are together, true? Perfect. For now, this is enough. For now, this is enough. This one, I will move it later on. And we want to compute forecasts rapidly, true? This is basically essentially my forecast. I want to be able to compute the forecast very fast if I want to be online, true? Real time, excellent. So the essential question that we want to answer whenever we do model predictive control is, what will be my forecast given that we start at a certain point and given that we use a certain input, okay? And we saw that for first order systems up to now, we have the total response is going to be equal to what? The free evolution plus the forced response. True? And this one is what? This one is the convolution between the impulse response that is going to be BEI80 for t bigger than 0, 0 otherwise. True? And we have an input, and we do the convolution. So for first order systems, y dot is equal to ay plus bu. This one is our h of t. Are we together? Are we together up to now, people? 1, 2, 3. We didn't see how. We are going to see very fast why this is the solution. This one is our free evolution. This one is our u convoluted h. How much are we together, people? 1, 2, 3. From a numerical perspective, if I want to compute this integral here, what do I need to do? I need to do a sum, true? And every time that we move the impulse response, we need to recompute the integral. Computationally speaking, do you see that this stuff here is expensive? It's a sum, true? And every time that we shift, we need to redo it. We want a way to compute this one in a faster way. This one is a table. It's a lookup table. True? This one is a lookup table. This one not. We need a way to solve that stuff in a fast way. Tell me if we are together. Read and tell me if we are together. Perfect. That's why. Laplace transforms will enable us doing this computation extremely fast. So, Laplace transform, well, one thing, just to be sure that we connect also with the other courses. In this course here, we use Laplace transforms to compute the forecasts. In other courses, you're going to use Laplace transforms to determine u, okay? In all the other courses, Laplace transforms, you can use them for computing both, okay? So in a certain sense, in this course, we have a focus here on creating forecasts, not on selecting inputs. But Laplace transform is something that is pervasive of automatic control, okay? So I'm giving a specific cut. In this course, you will hear me talking about this forecast. Watch out that the forecast is not only the unique thing that you can use, or better, there is not the unique thing for which Laplace transform is useful for, okay? Perfect. Let's start with the hypothesis. So let's define a Laplace transform. Maybe I do another video. I do kind of 2 videos so that we do